Okay, fine. Yeah. Yeah. Good afternoon, everyone. So we'll be starting with the third session of third day. So today's we have two speakers today for hands-on session. We have Archit Srivastava, and he is a senior researcher and co-founder of CIRQUIT Quantum Research at RVCE. And in the field of quantum computing, Chit has explored the areas of quantum algorithms, cryptography, um, quantum annealing, quantum machine learning, quantum hardware. He has worked with Boson Q PSI Private Limited as a quantum computing intern, performing R&D in the field of applying quantum computing methods to solve CFD equations. So along with these, he has participated in various national and international level hackathons, workshops, and summer schools being conducted by leading firms like IBM and Google. So his recent works of Archit mainly focused on the subdomain of quantum cryptography, quantum hardware, and quantum finance, with the conference papers and preprints being published in the aforementioned fields. So, and also he has written many papers and book chapters in the field of quantum computing in international conferences and journals. And currently he is intern in HP, and he has got placement offer in by September 2021. So we are actually happy to have you here, Archit, and I hope our attendees will be definitely benefited by your talk.
Thank you, ma'am, for this nice introduction.
Yeah. So we have next speaker. Just a minute, sir. Yeah. Just a minute, sir. I think my system got hung. 2 minutes, sir.
What happened, Sharwani?
Just a minute, sir. I think it got
Okay.
hung. 1 second.
Okay.
Just a minute.
Okay. Okay. You're audible. Yeah.
Developer in Qiskit, and is presently a researcher at CIRQUIT, working in the fields of quantum algorithms and quantum communications. His hobbies include photography and motorsports. I welcome you also, Ansh, for this afternoon session. Yeah, I think over to you both, Archit and Ansh.
Okay, ma'am. So shall I start sharing my screen?
Yes, yes, you can do it.
So is my screen visible now?
Yes, yes, Archit.
Okay. So first of all, good afternoon, everyone. And it is my pleasure being present in front of you and trying to explain you this topic. So just giving a brief about the topic that I'll be going through today. The name of the topic is quantum key distribution, and it is one of the major algorithms that has been implemented and is being into extensive research today. And a lot of research and development work is going on around across the globe in this field. And to achieve this, a lot of institutes and organizations are working extensively in this. So uh, talking about what I'll be covering in this session today is I'll be trying to go through the gist of what this algorithm is and how we can implement this algorithm using current quantum computational frameworks that are available. And specifically speaking, today we'll be using Qiskit, being provided by IBM. Just for a brief of Qiskit, so Qiskit is the quantum computational framework being provided by IBM to all the users across globe, and it gives us advantage and other benefits so that the users can develop their own algorithms and implement different protocols. So now coming to what the whole this quantum key distribution algorithm is. So in today's world, we actually have a lot of news and lot of discussion going on around how the security will be of our information, be it personal or professional information. And there are a lot of things that go on around, and many organizations have been there in huge controversies regarding this same about whether the information of an individual is secure or not, and the lack of the fear of like outsourcing of personal information of an individual is what is one of the major concerns in today's world, as we are moving towards almost all digital forms of communication. So it becomes a really important parameter. So the quantum key distribution is a protocol which uses the advantage of quantum computing and quantum physics, uh, and it then helps us to detect whether the message that we are sharing, is it being uh, trapped by a third party or not. Not trapped, actually tapped by a third party or not. And by getting to know whether the message is being monitored by a third party apart from the two individuals communicating, we can then develop on that particular risk, that whether we want to change the communication channel, or we want to eliminate that, or develop steps and measures to avoid that. So based on this principle only, the whole quantum key distribution algorithm was developed. So so what happens in this algorithm is, there are two individuals, say their name is Alice and Bob, and they are trying to communicate with each other, and and they are trying to share a secret information between themselves, and through an insecure channel. So there is a really high chance that there is a third person involved, which is trying to get the secret message from that channel, which Alice and Bob are trying to communicate between them. So what and let us name that third party as Eve. So what happens in this protocol is, Alice is having her secret message, and then she prepares the secret message. She encodes the secret message in a particular basis, in a particular random basis. Then she sends the encoded message to Bob. Bob then decodes the message using his own random basis, and then after decoding, he measures those basis, and then gets back the message. Then Alice and Bob compare both of their messages that they have received, and then they eliminate the bits which are not matching with each other, and and the bits which are matching with each other, they form their secret private key. So this particular secret private key is then shared to is then common with between both Alice and Bob, and then they can use this private key to encode and decode their messages for future, and the channel becomes secure. But so this was one case in which no interception was happening by Eve. But if an interception happens, so what actually occurs is Alice sends the encoded message over the insecure channel. Eve tries to measure the message and then using her own uh, basis. And so what this does, because the whole communication is happening via a quantum communication channel. So as we know that whenever we measure a quantum state, so it's the state in it either falls into the state of 0 or it falls into the state of 1. So there is the measurement that Bob will have after Eve measures the qubit prior to Bob getting the message. Bob will have a discrepancy in the probabilities that that the bits will that he will be receiving. So the result that Bob will be getting, it will create a disparity between the private keys, final private keys that Alice and Bob have. And once there is a disparity between the private keys of Alice and Bob, this will say that the channel is not secure and there is an eavesdropper in between the channel, and which is trying to intercept the message which is being transferred over the quantum communication channel. So this was a brief about how this happens. So I'll now go through how we'll implement this whole particular algorithm first first when there is no interception and the communication channel is clear, and then second when there is an eavesdropper present in the whole communication channel, and how it we'll see how it affects the whole algorithm. So as I have given the brief protocol overview, so for implementing this algorithm in Qiskit, so we need to first import few libraries. So that is the reason we first import quantum circuit from the Qiskit library, and this helps us to make quantum circuits and develop quantum circuits. The AIR is a backend simulator that Qiskit is providing, and these are the functions which will help us to run our jobs that we are creating. Then plot histogram and plot block multivector. So these two are visualization tools that will help us to get to know what the states are of a particular qubit and of that particular bit. And these are a few basic functions from NumPy. And so a int function helps us to create a random bit string or any random value that we want from the library from NumPy. And we have imported NumPy as NP. So after implementing this cell, we have imported all the libraries that we want. So as I was explaining that Alice first prepares her qubit states, and then she sends it over to Bob. So what does this mean? So it means that Alice is first preparing her qubit states of qubit state of plus, which is 0 in the x basis, and then Bob is measuring in the x basis. So Bob is confirmed that he'll measure 0 with 100% probability. So this is what is happening in this particular code block. So we first prepare the quantum circuit of one qubit and one classical bit. Then we apply a Hadamard gate, and then we provide a barrier. So this helps us to prepare the state of plus, which is the Alice's message after being encoded. So then now Alice sends this message over to Bob, and Bob measures it in the x basis. So for Bob will first apply a Hadamard gate and then measure the qubit and store it in the classical bit. So then what we do is we draw the circuit. So this is the circuit that we have, and then we send this circuit into the backend, which is the air simulator. So we use this particular command to develop the simulating environment, and then we prepare our job that is there, and then we send the simulation that we have created right now, and then we assemble it and run it in the simulator, and then the job that is prepared finally, we plot the histogram for it. So a histogram will help us to get the current state which is there, and help us to check whether we are getting the desired result or not. So according to the theory, the desired result should be that we should be measuring the state of 0 with 100% probability. So once the circuit is measured, so we see that the state of 0 is being measured with 100% probability. Now, so now we see that say suppose an eavesdropper tries to intercept the whole communication channel, and Eve measures the communication channel or the qubit before the message reaches Bob. So the same thing will happen first. First, Alice will prepare her qubit. First, Alice will prepare her state of the plus state by applying a harder market. And now, so if we look at this particular diagram, which is our current circuit that we are working with, so we see a measurement gate being present. So this is our Eve, which is trying to measure the whole circuit in the Z basis. So to measure the so as Eve intercepts the circuit in the before the message reaches Bob. So she applies this the dot measure function, and measures the qubit prior to the Bob measuring the qubit, and then Bob gets the altered message, and then Bob measures it in the X basis, and then we again display the circuit, make our simulation environment, create our job, and then based on the job we create our histogram count. So the inference that according to the theory, what should happen ideally is that as Eve measures the qubit, so the state that the qubit was prior loses its state, and the probabilities that Bob will with which Bob will be measuring decreases. So as Eve measures the qubit prior to Bob measuring it, so the probabilities drop at Bob's end to 50%. So Bob will then be measuring the qubits with a 50% chance of getting 0 and 50% chance of 1. So this is what the theory is trying, like theory explains to us. So once we look at the histogram result, so we get to know that the theory is in line with what we are implementing. So we are nearly the 50% mark in both 0 and 1. So these are the inference that we get, that we have a 50% chance of measuring 1 and 50% chance of measuring 0. So this tells us that there is something wrong in the channel, and some other measures need to be taken to correct this channel and reduce the risk of the whole information being outsourced to the eavesdropper. So now, this is what whole algorithm is working. So now diving a bit deeper into the whole algorithm. So we see what the step 1 is. So the step 1 is Alice chooses a string of random bits, and so Alice prepares a random bit string that she wants to share. Then she randomly chooses a basis of for each bit. So each bit is corresponding to one of the bases. So one is one is for Z, and this is a random basis that Alice prepares. Then what Alice does is Alice encodes each bit onto the string of the qubit and the basis that she chooses. So Alice then, after she prepares the basis and the bits that she has, she encodes the bits on the basis, and then she sends it over to Bob. Now, parallelly, what Bob should do to get the message correctly is Bob needs to first generate a random basis for his measurement. So Bob then generates a totally random basis, which is totally different from what the basis what Alice is using. So and these the Bob's result and Alice results are kept private to themselves, and they do not know about each other's basis up till now, because if these informations are outsourced on the same vulnerable channel, so there is no security of the message being transferred. Then after Bob prepares the basis, his random basis, he then measures the result in private. Then the results that Alice and Bob get, they publicly share these publicly share these bases which they use for each qubit. And after getting to know which basis each other have used, so they then get they can remove the bits which are not being which are not matching with both of them, and they can then generate their own private key, which they can use to encode information, the future messages that they want to send. So finally, the Bob and Alice share the sample of their random keys, and if they match, they can be sure that there is no eavesdropper in between the whole channel. So coming to the first example, which is the example without intersection. So now we look into the detail how the whole algorithm works and how to implement the whole this particular algorithm. So as we said that the step one to generate the random bits, we use the pseudo random keys. We use this randint function from NumPy, and here the seed is given provided as 0 to, so that while reproducing the results anywhere, yeah, the few initial messages the random string generates would be same. So coming to the step one, to generate the random set of bits, we use this particular. So this particular code block generates the random set of bits that is being used. So this particular function sets the seed value of the random function, and then we say that we want the bit string to be 100 bits long. So this 100-bit message will be sent through through a circuit which is 100 qubits long. So the first step, which is that Alice produces her bits that she is wanting. So the Alice bits is containing the bits, the random generated bit string that she is wanting to transfer. Then so now we parallelly compare what are the knowledge, what all things does Alice know, what all things are over there in the the communication channel, and what all Bob is knowing at that particular instance. So this particular table will be popping up throughout this notebook. So so at this moment, Alice has created her bit string that she's having. So Alice is now only knowing her what are her bits. Now Alice chooses to create encode these bits in X or Z basis at random, and to do that, we create another random like random basis for Alice. So so the case that we are using right now, this in the base 0 means that we are preparing the Z basis, and the 1 means that we are preparing the X basis. So we use the same random function, and then we generate the Alice basis, and we see that this is the basis which Alice is creating, random basis. So as you know that one is Z and 0 is X basis. So these are correspondingly Z X X Z X X X. So this is how it has been represented here. So now we know two things about. So Alice is having two knowledge of two things. So the first one is the Alice the bits which Alice is trying to communicate to Bob, and the second is the basis which Alice is having. So now we have the bits of Alice there, and we have the basis of Alice. So now we'll try to encode the whole message, and we'll try to see how that encode, what all um, uh, the encoded message look like. So for one particular qubit or one particular bit, we'll generate a separate a one particular quantum circuit. So for a length of 100 bit strings, there will be 100 qubits and 100 quantum circuits for each 100 quantum circuits in total. So being used to encode the message. So each qubit will be differently encoded, and so on. So this encode message does the function that we are trying to achieve. So what it does is that it takes in the number, the bits that that we are trying to encode, and it takes the basis through which we are trying to encode the bits. So we first create a message variable, and then a message variable list, and then we what we do is we first create the quantum circuit for that particular qubit. So if the basis one if that particular element of the basis is 0, so we prepare the Z basis, because this is the logic that we are following right now. So and if the bit is 0, we pass it, and if the bit is a 1, we create this, we add this X gate to the circuit at that point. Else, if the basis is 1, or we have to encode the bit in in the X basis. So we then apply we check whether if the bit is 0. So if the bit is 0, we apply a Hadamard gate, and if the bit is 1, then we apply an X gate followed by a Hadamard gate, and then we append the message, and then we return the list that we have generated. So now, because we have the encoded message function, now we apply that encoded message function to the random bits that we have generated. So now the Alice bits and Alice bases are being sent into the encoded message, and we have the encoded message right now with us. So to check whether this is working or not, so we see this first. We first print that the the zero index of the first both Alice bits and Alice bases. So we check that Alice at 0 we have the bit 0 and the basis is 1. So we should have this particular circuit. So when we check the first circuit of the message, we see that it is in accordance with what we are trying to see. So now we are sure that the algorithm up till this encode message is working fine. Now we move on with the table that we have. So now we have the message being created, and the message has been transferred to Bob. Now Bob creates a random basis for his measurement. So we again use the random function, and the steps up till now are the same steps that was explained above. So we first create the basis for Bob, and then we print the basis for Bob. So we get this random basis that Bob is trying to use, and now the knowledge table that we have is we have a message being transferred across the channel, and Bob is having the knowledge of his basis. So now we develop a measure function which will measure the message that is being transferred, that is being received by Bob, and then Bob will like store the measurement results that he has. So we for this function we have the first parameter as message and the second parameter as the basis of the Bob that is there. So we then develop because it is a measurement function, so we first develop our backend that we want to work with. So we are calling the air simulator backend, and then we initialize a measurements list. Then we see we see that if the basis is 0, so if the measuring basis is 0, so Bob will directly measure the qubit, and if the measuring basis is 1, so Bob will first apply a Hadamard gate and then measure the qubit. So now because we have our these functions created, so now we generate our this simulating environment. So we are calling the backend, and we are then applying then we are initializing the queue job that we want, and then we are going on with the result, and then we are measuring it, and then we are appending the hello.
No, Archit, there is one question from Kavita ma'am. If
Okay.
after you're finished, I think we can proceed with that.
Okay, well, sure. Then after the measurements, we append the measurement bit and then save it into the measurement list that we have. So this measurements then we return the measurements list. So after now we have created this particular function which helps Bob to actually measure the message and then save it into a parameter. And now what we do is we apply that particular function. So the steps above this particular function are the steps which has been explained above. So now when we apply measure underscore message function, so we store it into the variable of Bob's result, and we can see that the circuit of message 0, which is representing the 0th qubit, had an X measurement added to it by the Bob. So we first draw the message, the message which is there at the 0 index of the message being transferred, and then we see how Bob is measuring. So this is how Bob is measuring, and the result that the Bob is getting for for his message is this long string, and Bob keeps this result private. So now, again, coming to the knowledge table that Bob is having. So Bob is having his knowledge of his basis, and the Bob is having result. So now, after this, what Alice does is so Alice and Bob never reveal their results that they get. They only reveal the basis that they encoded the messages with. So if we look, Alice then reveals her encoded basis through the quantum channel, and Bob is now having the knowledge of Alice's basis. Then Bob shares his basis to Alice through the same quantum through the same Eve channel, and they get to know about each other's basis. Now because they are having the knowledge of each other's basis, so they can actually apply those same basis to the message to check whether the final message that they're getting or not. And so what happens is that because they to get to the private key that they should be using to generate their result transmit their messages. So they need to remove the bits which are not which are not in line with their final result. So this particular function, which is remove garbage function, takes the Alice's basis, takes the Bob's basis, and then the bits that are there. And it stores the final result, which is the good qubits in it. So what it does, is that if the Alice basis Alice basis is equal to the Bob basis, so it appends the bit and stores the result. So now we are there with all of our elements, and we prior to this step, we have explored the 3 steps of the whole algorithm. Now what we do is we apply this remove garbage function and get the Alice key, and we print this Alice's key. And we then have the same for we then have then Alice is having her knowledge of key, and then Bob applies the same function, and then Bob gets his key. So what theory suggests is that these 2 keys that are there, these 2 keys should be if there is no Eves proper in the channel, these 2 keys should be same for both Alice and Bob. So now the step 5 is that we'll make sure that the protocol work correctly. So we take what Alice and Bob do is that they broadcast their keys publicly, and their keys are they are no longer secret. And then what they do is what we do is uh, we then check whether their keys are same or not. So if there is no eavesdropper present, so these keys will match, and this is what we are seeing currently right now, because this was an example where there was no interception of the message. Now, this particular result states that the both the samples that Alice and Bob have, they both are in line, and there has been no eavesdropping in between the channel that has been created. Now, this says that the Bob sample and Alice samples are same, and this suggests that the algorithm has been correct, and the key that Alice and Bob have, they can now share the key to encrypt their messages.
Okay, can I permit Kavita ma'am to ask the question?
Yes, yes, ma'am.
Kavita ma'am, I have unmuted your. Can you please ask?
Yeah, sure. Archit, can you hear me?
Yes, ma'am.
Archit, my question is Eve a hacker?
Yes, ma'am. That can be a name given to Eve.
Okay, then while sending a message from sender end to the receiver end, why you are sending it to the Eve's channel?
So, ma'am, what happens is it is not an Eve's channel. It is a normal communication channel. It is only that Eve is because it is a normal communication channel. Say it is the internet connection between my computer and the server that is there in some other country. So the channel through which the information is being transferred, it is that normal channel, and anyone can tap into it and try to gather the information.
Okay, fine. By the table, I thought the message is sent over the Eve's channel, so that confused me. Okay,
No,
that
no.
was clear. And next, you said in the next session you will be adding eavesdropping in between the Alice and Bob.
Yes, ma'am. It is. I'll explain it in just 2
Okay,
minutes.
fine.
Yes, ma'am.
Then that's all my doubt. Thank you for
Okay.
answering.
Thank you,
Okay.
ma'am. Ma'am, shall I proceed?
I'll just ask audience. Is there any other question from attendees? Okay, there is one question from Sumati ma'am. She asked, does the key size be random or fixed?
Key size, ma'am, it can be it can be. It is based on what is the necessity. Uh, ma'am, key size, like I'm not sure what key size ma'am is uh, interpreting with.
Maybe number of photons we are using for communicating the key. Probably she is talking about number of qubits.
She says
Okay.
n is equal to 100.
Can
Okay.
For example, n is equal to 100 sample.
in the classical cryptography, we talk about 1024 bits and all. No, probably in that sense, this question is asked.
Okay, sir. So the number n that is there in this particular algorithm, so this number is representing the number of bits in which we are trying to transmit the message over. So this is in accordance with the need of the type of the size of the communication that we want to make. So we can actually reduce this number to 50, to 10, or even to 1,000. But this number is constrained to the actual quantum computer that is being used. Because right now having this number n is equal to 100 is also not a viable option because of the hardware constraints that are there in today's system. But in future, I think like we'll get this number more realistic, and maybe in other, let's say, even 1,000 qubits all can be a reality. So this totally depends upon the users that are trying to communicate between them.
Would the distance be a matter? For example, if you take a QKD, if the two parties are hundreds of kilometers away, if you look into the size of the key and all. Is there any link between the distance of communication and this factor?
Yes, sir. So the distance is actually a really big parameter which plays an important role because we are dealing with quantum states, and holding on to the quantum states is a really difficult task even for technologies that are present today. So there have been like the distance over which QKD can be implemented. If I'm not wrong, today I think it is 400 kilometers, which was implemented by a group of scientists in China. I'm not sure about this information. I need to cross check it once. But yes, sir, distance plays a major role. Uh, so,
I think you
sir,
can
can I
proceed,
proceed?
Archit.
Okay, okay, sure. So now we have completed the first aspect of the whole implementation of QKD thing. So that was an ideal situation where there was no eavesdropper, and we were getting this ideal result that we were trying to achieve, and that the final key that we are getting, it is the length is similar, and there is no discrepancy, and all bits are in line, and this can be used. Both Alice and Bob they can use it as a private key, and the channel is secure. Now, what happens if we have the eavesdropper in trying to intercept the message in between? So the steps that we have discussed above are the same steps that go into this initially. So first, Alice prepares a random number of bits. So she generates the bits that she will be transferring, and then we get this bit string of 100 of n is equal to 100, and then she prepares her random basis that she'll be measuring. So one will be a 0 will be corresponding to Z, and 1 will be corresponding to X, and this will the basis in which Alice will be uh, encoding her message through the channel for Bob through the channel. So now Alice is having a knowledge about her basis and her bits that she wants. Now we to check the correctness of the things that we have prepared up till now. So we check how the circuit looks like. So we check the first index of the message, and we draw the circuit. So we get this particular circuit, and we are sure that up till now everything is fine, everything is working fine. But now what happens is the channel through which Eve is sending her, Alice is sending her message to Bob. So there is this interception being created by Eve, or Eve actually can record as a hacker.
Yeah,
Hello?
Archit, before that, there are two questions. Can I ask?
Yes, ma'am.
Yeah, two questions from attendees. Should distance matter in case of entangled photons? I think that is what Satish Babu sir asked.
Yes, ma'am.
Okay, so madam, this question was answered by him. Should we repeat again? Okay, the next question is it possible that number of qubit, no qubit is matching after passing through bases? That is, within bracket, they have mentioned as polarizer in case of photons in key generation process.
Ma'am, can you repeat the question once again?
Yeah. Is it possible that no qubit is matching after passing through bases in key generation process?
Okay.
So within bracket, for the basis, they have mentioned as polarizer in case of photons.
Polarizer in case of photons. So actually, I'm not sure about what actual answer of this question is, but if we are talking about probabilities, so if there is an eavesdropper in between, so there is a high chance that no particular result will match at Bob's and at Alice's end. So I'm not sure whether this answer is correct or not, but I'll also look into it when we are talking, because because this answer changes when we look into the photonics aspect of the whole QPD protocol. So I need to look into it.
Okay, not an issue. I think you can proceed.
Okay, sure. So now, Alice is having her initial message and basis created. So now what happens is there is an Eve which is trying to intercept the whole message and trying to read what Alice is sending to Bob. And Eve can be called also as a hacker. And so now what Eve does is Eve actually measures. So the measure message function that we created above. So Eve uses that function to measure the message that is being there, and we store that message into the intercepted message. So now we have the intercepted message. So we get the encoded message that Alice was trying to share to Bob through the channel, but Eve has now now intercepted the whole communication channel and measured it. So now what happens to the message is that the 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 states that Alice was sharing to Bob. So the probabilities of Bob measuring them actually reduces. So Bob will have a probability of measuring the state of 50% probability of getting 0 and 50% probability of getting 1. So now we now randomly draw the circuit, and then we see that this is the current state is. Now what happens is that even the message that Eve has intercepted is then transmitted to Bob, and Bob measures that message randomly, and then according to the choice of his basis that he is creating randomly, and then Bob checks whether his what the state of his message is. So up till now, Eve has so Alice has created her basis and message, and then Eve has tried to measure tried to intercept the message and kept the intercepted message, and then Bob tries to generate the basis, and then Bob tries to measure the message. So now, what we have is an the final state of how message looks like it is something like this. So if we see the first index of the message, we get this that Alice has prepared the state. Eve is there, which has measured the message, and then we have Bob measuring the state that is there. So now going because up till now, Alice and Bob are not having the knowledge that Eve is present in the channel. So Alice and Bob are unaware about this interception, and what Bob and Alice go according to the protocol that was there. So up till now, Bob has received the message, and now what they do is they reveal their basis choices and discard the useless ones. So this is what the step 4 of the algorithm was. So after Bob measures the result, so Bob generates his key by removing the garbage values, and then Alice generates her key by removing the garbage values. So now, after generating the Bob and after generating their keys, Bob and Alice compare the same random selection of their keys with, uh, to check whether the qubits were intercepted. So up till this point, Bob and Alice are not having uh, mm, any knowledge about whether their message has been intercepted or not, and they compare the random selection of keys. So when they check these, when they create the sample size and get the sample keys that they want, so they check they get these two particular lists, and on comparison of this particular list, whether the Bob sample or Alice sample is true or like same or not, we get the result as false. So what this result is inferring that uh, Bob's key and Alice's keys do not match, and this tells what this information infers to Bob and Alice is that there is a third party involved in between the whole communication channel, which is trying to intercept the message which is being transmitted through it. And this actually uh, uh, helps both of them to then work upon either changing the whole communication channel itself to securely transmit the message, or coming up with certain protocols or measures in the same communication channel, which they can which they can further try to prevent the eavesdropper in that message and avoid the secret message that is being transferred being vulnerable to these kind of attacks. So uh, this is how the whole algorithm of QKD, whole protocol of QKD looks like when it is being implemented in Qiskit. And how this is used in today's world is that it is used for something known as risk analysis in many firms, and because secure communication is one of the most important aspect for any organization, be it a government organization, a private organization, or any other, and even for an individual. So getting hold of this particular protocol and implementing these protocol will eventually become a necessity for all the organization, because there will be counter algorithms being developed to. So this was a protocol, an algorithm to secure a communication channel, and there are counter protocols being developed in quantum computing to disrupt that communication channel and get the encoded message. So one of those algorithms is the Shor's factoring algorithm. So Shor's factoring algorithm, which Ansh will be explaining in the next in the after 5 or 6 minutes. So that algorithm actually is it is a really important algorithm, but uh, it is actually an algorithm which if it goes into some a person which is having not right intention, so they can use it to break encryption standards like RSA-86 or RSA-5112, and they are so to be to have those security measures and methods being implemented. These type of algorithms like quantum key distribution algorithms and other algorithms are being intensively researched and developed. So currently in India, also Raman Research Institute and Bhabha Atomic Research Center, and these all organizations are working intensively in this field, and they have actually implemented the QKD protocol, and ISRO is also working intensively. So um, yes, I think this was the quantum key distribution protocol, and so for if anyone wants to look in more detail about specific algorithms, so there are algorithms named as BB84 protocol and B92 protocol, and these algorithms are developed on this particular concept, and they are used to implement these kind of protocols that are being discussed. And I think then I would like to conclude this particular session.
Yeah, thank you, Archit. I think now Ansh will carry on with the next session.
Yes, sir. I'm stopping my screen.
Yeah. Any question to Archit? Okay, you can share the screen, Ansh. You can carry on.
Yes, ma'am. Ma'am, could you just allow me to share my screen? I think the option to. Am I audible, ma'am?
Yes, Ansh.
Yes, ma'am. I'm not getting the option
Yeah,
to
yeah.
share screen.
Sharman, it's just drag that share thing.
Oh, yeah. Yes, yes, I forgot. I
Yeah,
forgot.
okay.
Yeah.
Yeah, got it. Yeah, the screen is visible.
Yes.
Okay, so start with Shor's algorithm.
Voice is breaking, Ansh.
So Archit just mentioned Shor's algorithm has okay. Just turn off. Yeah. Yeah. As to start over again, as Archit mentioned in the previous session, that Shor's algorithm has the potential to basically disrupt world cryptography. So that's what we will look at as to how Shor can do that. So before we go into Shor's algorithm, there are a few prerequisites that we need to understand. More specifically, it's the QFT and QP algorithms. So QFT, or the quantum Fourier transform, is the quantum analog of the classical Fourier transform, or the fast Fourier transform, as some of the participants may know. So the functioning of quantum Fourier transform is actually very similar to what happens in the classical case. Again, over here, as in the classical case, the Fourier transform converts certain, say, values from the time domain of the function, from the time domain to the frequency domain, and vice versa, in, say, for grid analysis and optimization, stuff like that. In the quantum case, the Fourier transform, the quantum Fourier transform, is used to change basis of a certain state. So I won't be going into a lot of depth of the code of QFT and E, so that we can spend more time on Shor's and Grover's algorithms. So I'll just show you how and what does QFT do. Okay, so I want you to focus on, I'll be running this cell right now, and I want you to focus on these top qubits here. And these are, okay, so these are the outputs of the QFT, and these are the inputs. So when I run the circuit, the program will basically give it all the inputs from 0 to 15, basically the 4-bit input. And we will see how QFT basically maps the input with it. So, yeah. You can see over here, notice that the qubits on top are basically rotating in the XY plane. So the qubit 0 is rotating at some angular velocity, and qubit 1 is rotating at a faster velocity. It's rotating in the same direction, but at a faster velocity. Qubit 2 is even faster, and qubit 3 is almost pi by 2 pi radians per input. The input is basically the normal that we see for a 4-bit input, the 000000001 and stuff like that. So what we see over here, the effect of QFT is basically to convert this input from the basis of, from the Z basis, this is Z base, the word is Z basis over here, to the angle of the, to the, basically the rotation angle on the XY basis. So I'll just run it again. It's a bit more clear to us. Yeah, so you can see that it's rotating. So each configuration of all 4 of these rotations corresponds to a specific input. So that's what QFT does. It is basically just mapping the input on a regular input to the frequency of rotations on the XY plane for the same qubits. So that is the effect of QFT, and that's kind of the motivation behind what it does. And it also is also similar to what we see in the classical case, since classical also maps time domain, frequency domain. So that's similar what's happening here. More specifically, it's converting the Z-axis qubits to the X-axis qubits. X-axis being this over here, or the XY plane of the atom basis. Okay, so that was about QFT. This is the circuit over here. I won't be going deep into the circuit for QFT. We're doing this notebook video so you can have a look at how this circuit has been implemented. So we'll move on to quantum phase estimation. First of all, are there any doubts regarding what QFT does? I guess this was pretty self-explanatory. Then no doubts, we'll move on. Okay, so move on to QPE, or quantum phase estimation. So, okay, this is an example. Suppose you have a unitary U, and you operate the unitary U on some state side, such that the state psi is an eigenstate of the unitary Q. Right. So what does an eigenstate mean over here? It's basically that the state psi or the vector psi is an eigenvector of the unitary or the matrix, unitary matrix formed by this operator U over here. Excuse me. When you operate a U on psi, you will get a form similar to what we see in the RHS, which is basically some constant or the eigenvalue times the eigenstate. So we've already seen this form quite a lot in math, and I'm sure you must be used to it. So this over here represents the eigenstate of psi with respect to this unitary. And what QP does is to estimate this theta. So it's estimating the phase of the eigenvalue that this eigenstate has for this unitary. Okay, so again, I won't go into the code. I'll just take you through how it works. So this is the circuit. Just to gain some intuition as to how it's working, is that we are reverse engineering QFT over here. So all of these gates over here are the same unitary U applied different number of times. Unitary times 1 applied on the first qubit, unit times 2 applied on the second qubit, and so on up to 120. So mathematically, what we're doing is we are basically reverse engineering QFT. So we are creating QFT by using these circuits, and then like QFT inverse, it is basically the same circuit that we saw above, just reversed. And then after all these operations, what you get out of this is basically the state theta times 2 power n. So when you measure it, that's what you get as an output. And then you simply divide 2 power n from the output, you'll get theta. So to run the circuit over here, as you see, we have applied a phase of pi by 4 over here on this gate, and then we apply the input state x or the one state, which is an eigenstate of this specific unitary. When we execute this cell, get that the phase applied by this gate on the eigenstate is pi by 4. Again, you can change this to say pi by 8. You'll get a different. Now, how do we select the number of qubits over here? So that depends on what accuracy you want to achieve. Right. So if you want, of course, these are not integers, right? And what you get as an output over here is going to be integer. So to get the most accurate value, you need to increase the number of qubits. As an example, let's take say 5 qubits over here and 6. And this circuit, we got 0.1875. Now this is supposed to be 1/6 which is around 0.166. So this is actually pretty wrong, right? But if I increase the number of qubits in the counting register, this is the counting register above, and this is the gate or the ancillary register. So if I execute this with a larger number of qubits, yes, we see that it's getting closer to the 0.1666. So again, if we increase the number of qubits further, you get an even better accuracy. I won't be executing it for any large number of qubits because these are actually very computationally expensive operations to be running on a classical computer, and increasing the number of qubits will actually require a lot of time for execution. So just to save some time out there, we'll just suffice with this 0.16, and assuming that a large number of qubits will give it better accuracy, reaching closer to the 0.166 value. Okay, yeah, so this is what was the most important takeaway. If there's one thing that was the key takeaway from this notebook, is that QP has the following form: is U psi being eigenstate of U, will ultimately give you e power pi I theta times psi. The theta is the phase estimated. So before moving forward, are there any doubts regarding around QFT or QP? I know there was a little bit rushed because we need a bit more of time for shorts in so just talk about the intuition as to what these circuits do and how, not exactly how they work, but at least their functions. Are there any doubts regarding this?
Any doubt from attendees? I think you can proceed, Ansh.
Okay. Okay, so now that we have QFT and QP out of the way, we'll talk about shorts. Okay, so we already saw that given some unitary U, QP estimates theta for 2 pi theta psi. Okay, suppose you have a unitary which, when operated on some state, say y, ultimately gives you the state A times y mod.
Yeah, Ansh, one question from Shabana Chakravarti madam. She wants to know the advantages of QFT.
Okay, so ma'am, QFT is often used as a very important subroutine in several quantum algorithms. So if you see that QFT was actually used as a subroutine over here in QPE, QFT also works very similar to the normal Fourier transform that we have in the classical sense, but you can't get the same values out of it because we have some measurement constraints in quantum computing since because of the projective measurements that we have, which destroy a lot of information that the qubits store. So yes, that kind of limits the applications of QFT in its direct sense as using it as a Fourier transform, but it is very often used as subroutines of several algorithms, as we'll see in short. I hope that answers the question.
Yeah, I think you can proceed now.
Okay. Okay, so coming back to short algorithm, and we said that we have a unitary which an operator on y gives you a y mod n. Now, talking about a number theory, just a brief number theory. Suppose you have a form a mod n, and then you apply and you have suppose you have a power r mod n such that a and n are both co-primes, they don't have any common factors, and r is the smallest integer number such that a power r mod n is equal to 1. Now a mod n does not have to be equal to 1. It's not, of course, not going to be equal to 1, otherwise r would simply be 1. But for some random r, a power r mod n is equal, and we want to find this r. Now this is not a very trivial problem, and you'll see why. Because if this would have been the case, if this estimating this would have been an easy problem, factoring large numbers would have been pretty easy. Okay, so coming back to the unitary, we said that uy ultimately gives you a y mod n. So applying the unitary to the state 1 over and over again will give you u of 1 gives you 1 into a mod n. U square will give you a square mod n, and u power r will ultimately give you a power r mod. And as we saw above, that a power r mod n is equal to 1. This will ultimately give you 1 again. So you can see that there's a cyclic nature that this a power r mod n has. That we started from u of 1, and then applying this state over and over and over again, we get the state 1. So that yeah, again, starting like starting from u bar 0 of the state 1, you applied r times, you get the state. So that's what we want to do. We want to find the period of this cycle after which the values start repeating. So that's why Shor's algorithm is actually very often known as a period finding algorithm rather than a factorization. So we'll see why is it called period finding. Okay. So what can we do with this? We have this information. We need to estimate this R over here. How can we go about this? Let's take a superposition of all of these states. Let's just, we have a bunch of states over here. Let's just try and take a superposition of all of the states. So we call it U0, and it's an equal superposition. That's why we have 1 upon root of R, and K going from 0 to R minus 1. We have A power K. So we do all of these states over here, and we put in a superposition. Right. Now, if you apply the unitary U on both sides, due to linearity, due to quantum operations being linear, the U can be taken inside the summation, and then you will have U of A power K mod n. And since this is cyclic, every U of A power K mod n would be mapped to some other A power K, some unique A power K dash mod n, for example. That's what's mentioned over here. Actually, when if you sum the transformed summation again, you will get U0 back. So basically what that means is that if you apply U over here, U of U0, you get U0 back. So what that means is that U0 is an eigenstate of the unitary. Only that the eigenvalue for this eigenstate corresponding to the unitary U is 1. So just to recap, we put in the superposition, we apply the unitary U on both sides, and we get U0 back with the eigenstate 1. So the eigenstate being 1 does not really, we didn't get much information. So what can we do? To exploit some advantage out of this summation over here, we need to exploit some properties, say interference. Right? So for interference, we need phases. Therefore, we apply phases on the states inside the summation, and the phases are all proportional to the k that we see over. So ultimately, we created a new state, say U1, which is again an equal superposition of states a bar k mod n with a phase e power minus 2 pi I k. So why do we have the divide by r over here? So that every state inside the summation is at an equal phase from each other. So basically, between any two consecutive case, the phase difference between the states would be 2 pi I. So that is the basic objective behind putting the r in the denominator. Right. So again, we would apply the unitary on both sides to see how it can help us, and it is observed based on the reasons again. So I won't be going into how this came about. I guess it should be going to the theory sessions, and so the lab will just use it as a result that applying the unitary u on Q1 will ultimately give you e power 2 by I by r. Right. So we have some phase now. If you see, this is a little similar to what we saw in the QPE equation. Basically, if you go back to QPE, the equation of QPE was u psi is equal to e power 2 by I theta psi. So this is again very similar to that. It's u psi equal to e power 2 by I, theta being 1 upon r over here, and psi. So if we simply run QP on this equation over here with the input state U1 and the unitary U, we should get 1 by R as an output, right? Because that's what QP does. So problem solved, we have R, so we can use it to factorize it. But the problem with this is that this state U1 over here is not easy to realize. You cannot just realize any quantum state. It's complex. The number of gates required to form a quantum state might not be that small, and it gets really complex to create arbitrary quantum states. So we need to simplify this or generalize this. Okay, so we apply, we change this state over here, and we generalize it by multiplying an S. And S also ranges from S equal to 0 to R minus 1. So when we generalize it as US, is 1 upon root R, again it's an equal superposition, times e power minus 2 pi ISK by R. So S is this is 1 upon that. So there are total of R, U, S is possible now. And this remains the same. Again, applying the unitary both sides, this we have is U of US is equal to 2 pi IS by R. Right. So this time there's a bit of a difference. You have an S over here as well. So this can also be used, but again, estimating US, creating the state US is also pretty different. So if we take the superposition of all of these states US, what we do is basically 1 upon root of R summation S equal to 0 to R minus 1 US, and simplify it further. This is the entire is going to give us is summation of summation over S and summation over K, and then the state inside. Summating this over and over and doing the math over there will ultimately give you 1. Now this we can pretty easily realize. We couldn't realize S, we couldn't realize U1, U0 wasn't really helpful. but summation of US is realizable. So now the equation that we have over here is if we apply the unitary U on the state 1, you're basically applying the unitary U on the equal superposition of the possible states US, which is this, and ultimately you will get this final equation. So now if we try to run QE on this circuit, you will get S by R, but you don't know for what S. So the output is a superposition of all possible S's for S by R. So you can still estimate S, but you don't know what, you can still estimate R using 2PE over here, but you don't know what S you are going to get. So that's going to change our measurements, and we'll see how does that affect our measurements. Okay, so coming to, so now we have the theory out of the way, coming to the practical part. Okay, importing of the libraries, these are pretty common libraries that we have all used a lot now. Okay, so QP is the basis for short value, as we have already seen. And for running QP, you need two blocks. You need two things. You need the unitary, which applies the phase, and you need the initial state, or which is basically an eigenstate of that. Okay, so talking about the unitary for the model, coming to the unitary, which is basically U. We just assumed that we have a U, but we need to realize it somehow, right? Which is basically a transformation that U gives you, is this unitary U of y equal to A by mod. So this is the definition of that unitary. So this looks a little complicated, I know, and it is this is not a generalized unitary for say any A and any N. This is something very specific to N to 15, and A being one of these values. So for any such N or A, we will have to work out a new for a new unitary or a new oracle, as we may call it, and then we have to create a unitary for that. Now, how does this work is basically how the math works out. There is a bit of explanation over here, which we will come back later if we have some time in this session. We're short on time right now. So after covering short algorithm, we'll come back to this. For now, let's just assume that this operates similar to what we saw over here, which is U of y equal to A. Let's just assume that this unitary is doing the function as integrated. Okay. Now that we have the unitary, let's talk about the initial state. And as we saw over here, for creating the initial state, all you need is the one state. So we have the initial state already, and it's pretty simple, simply the one state. So now we have the unitary over here, and we also have the initial. Now we can go on proceeding and building the QP circuit. So we define the number of QP bits, which, as we saw in the QP circuit, is basically notes the accuracy with which the phase can be estimated through the QP circuit. And A, which is the number over here, A, is 7. We take it to be 7 over here, but A has the constraint that A needs to be smaller than, and it needs to be co-primed with N for the algorithm to work. It can be any number. So as you saw over here, A can be any of 2, 7, 8, 11, and 13. So all of these are co-primed with 15 and a smaller. So A can be any number between these. The choice of A would change the answer that. So we'll see A affect the ultimate function of the algorithm later. Okay. So just creating the QP circuit, we already saw in the QPD circuit what all you need is these unitaries. You need the initial state, you need the Hadamard gates, you need the QFT transfer operations. So we'll do that all over again. We need the QFT dagger, which is the QFT inverse. Dagger is basically inverse for unitaries. That's basically the conjugate first, which is applied over here. So we create the QFT inverse, the QFT dagger, and then we take the entire circuit and we implement it. You can see the similarity between this circuit and this circuit. So there's one difference that you might notice, that this unitaries over here are applied only for a single qubit over here. But in this case, it has been generalized to work on multiple input states. So that also the number of qubits over here depends on P. So since our n in our case is 15, so we need 4 qubits to represent that, which is 1111. If you have a larger n, say 20, you will need 5 bits for representing the same here. However, the initial state will still remain the same with the x qubit, with the x gate being on the last qubit, which basically means the 1 state. Okay, so we have the circuit with us. Okay, first of all, are there any doubts up till the definition of the circuit over here? Okay, there's a none. I think we should move on. Okay, so we have our QP circuit. So let's go on to make some measurements. So again, we have several times since yesterday, and once you make measurements, you will get some values out. Right now, we saw in QP, we were only supposed to get one value out of it, right, which corresponded to the phase. Why are we getting such a distribution of values? Why are we getting multiple values? There's just one phase. So why are we getting multiple values? It is because of the S that, as we saw, that output is going to be a superposition of multiple S by Rs depending on S. So this S is what is creating this multiple outcomes that you see. So all of these correspond to different values of S. R still remains the same. Right. So now you have a measurement outcome, which is basically S by R times 2 power n. So we need the S by R out of that so that we can estimate R. So what we do is simply divide the measurement outcomes, divide all of these by 2 power n, in which in our case is basically just 2 power 8. And this is the code for that. It's just a number of qubits. You divide it by that, and then we represent all of them over here. So yeah, so resistor over there in binary was these, and the outputs in decimal were that. And then dividing them by 2 by 8, you'll get these phases. All of these correspond to S by R. Phi is equal to S by R over. Now you have the value, you have the ratio between S by R, but how do you find the exact S and the exact R? So that is done through something known as the continuous fractions. So basically, you try to decompose the fractions to get the most accurate values for the different denominator with no common factors out through simply only through its ratio. So Python has this functionality embedded directly to run the continuous fractions method. So it's run through this statement over here. We run the fraction continuous factor on the phase values that we obtained, and we limit the denominator to 15 because the maximum value of R that you can have is 15, because we only range from 1 to 15, because n is equal to 15. I will limit our denominator over there. And again, just to represent it, we write them down. So this is the phase values that we got by the fractions through the continuous fractions method. So for 0 phase, you get a 0 by 1. For 0.25, you get a 1 by 4. For 0.5, you get 1 by 2. And for 0.5, you get 3. And the guesses for R for corresponding to all of these would be 1, 4, 2, and 4. So these are basically just the denominators what you get from the continuous fractions method. Okay, so now we see depending on R, we are getting different value. Depending on S, we are getting different values of R. Why is that? So I mean, how does that make sense? R is just one specific number, right? Value. The reason for that is, suppose S is a random number from 0 to 1, and if S and R have any factors in common, then those factors would be cancelled out during the continuous fractions. So it will ultimately give you a simplified fraction, such that S and R are both simplified by those factors, and then this R would correspond to that simplified version of the fraction rather than the original one that we were expecting. So therefore, after making a measurement, you're not really sure whether the value you got is correct or not, since it's random. So if so you got to check if that the R that you received is correct or not, and if it's not, you will try again. If it's correct, well. So how do you check if the value for R that you receive is correct or not? So for that, you simply factor the number. Try the R, you get R, and then you try to factor number using that value. Okay, so how do you factor it now? Suppose, okay, starting on the start again. So you have A equal to 7, A equal to 15, just to reiterate, and the GCD of 7 is 1, just to state that A and N are supposed to be co-primes. We run the entire circuit again, which is the function defining the entire circuit. So we're going to run it again. So yeah, so we're going to run the entire circuit again. You don't have to use the above functions. And then after running the entire circuit and running the continuous fractions method, you get some value R equal to 4. After running the end circuit, doing everything that we discussed till now, you get a value of R equal to 4. What now? How do you know whether this gives you the correct factor of N or not? So this is something that Shor himself worked out in and presented his paper when he was presenting Shor's algorithm. So what is that A bar R mod N is equal to 1? That is that we saw in the very beginning, that this is what brings about the cyclic nature of this function, that A bar R mod N equal to 1. So of course the 1 is also in mod N basis. So you can bring this 1 to the left hand side, and then this basically means A bar R minus 1 whole mod N is equal to 0. Right? Now, after this, you can decompose this into A bar R minus 1 is equal to A bar R by 2 minus 1 into A bar R by 2 plus 1, given that R is even. This is applicable only if R is even. If it's odd, we'll see what else can we do if R turns out to be odd. Now we see that we have A bar R by 2 minus 1 into A bar R by 2 plus 1 mod N is equal to 0. So this means that either one of A bar R by 2 minus 1 or A bar R by 2 plus 1 has to be a factor of N. So when you have an R, which turns out to be even, and when you plug it into this equation, and if you get 0, it's that either one of them is actually a factor, so that you can simply find these two and then actually divide by N to see if it's actually divisible or not. Right. So after running entire algorithm, we got a value of R. We plug it into the value over here, A bar R by 2 minus 1, A bar R by 2 plus 1 mod 0, just to check, and then we print out the guesses that we get that we found this. The GCD is basically checking if there are any common factors between N and the guess that you have, and you find that the guesses are 3 and 5. So you see that we started off with the number 15 as our N, and we got the possible guesses here. So we got the result out in the first shot, that the guesses are 3 and 5, and they actually turn out to be correct. But this is not always going to be the case, obviously, since we saw there are two things that could go wrong over here. First of all, the value of S we receive may not be co-prime with R, and there may be some common factors which might cancel out during the continuous fractions method, and which will give you a value of R. So you're starting off with the wrong value of R to start off with, and then all subsequent calculations would most certainly go wrong. One contingency is when you've got the wrong S, which is not co-prime with R. And second is that if the R that you ultimately receive from the continuous fractions method is actually odd, then you cannot use this relation over here. So that also halts the algorithm, and you'll have to go all the way back, run the entire circuit again, and then just try it. There is no alternative. Okay, so yeah, so we saw two occurrences in the algorithm can fail. So what are the solutions? The plain simple solution is try again. you can't really do anything about these. These are going to occur, and the only solution is track it. So you can do two things. Either just apply directly. You think that there has been some problem with the value of S, so you execute the same exactly same circuit again, and you get a new value of R. You plug it in, and it's correct. If not, and you think that S is not being the problem, there's some other problem. You change the value of A, as we saw again that A is something we chose in this case from this list. We choose another value of A and then run this entire circuit again to check if we could possibly get a correct S and then get a correct R out of it. Then find that this is a factor. So yeah, those are basically the contingencies that you can have inside algorithm when S is wrong or when R is wrong or when A is wrong, and then the only solution that you have for all of these problems is that. Okay, so again, taking all of these in consideration, we have chosen an A equal to 7 over here, and we have chosen our N equal to 15. And then we run the entire circuit until we get the correct value of S, which can give us the factors. So, for example, over here we got the value 3,5 for our S. Over here, when I ran this circuit before, I got guess factors 3 and 1. Now, 1, though technically is a factor, it's a trivial factor and doesn't really give us any help. So factor found was not 1 because it's already only factor found was 3. So we can run this again. I hope this works. Yes. So we found it in the first attempt. This is not going to be the case. You might have some other factors that you might get inside the first go. Again, we got 3 and 1, from which 3 was the only factor, was not considered a factor. Okay, so yeah, that was about, and we can also choose whatever value of A we might want to have. So just have whatever value that's allowed. This we have to say, but let's just take 8. Let's see what happens when we choose another A. So it turned out to be correct. So multiple values of A can correspond to the same factor, but that's not always going to be the case since it's a very small sample. Multiple A's are corresponding to the correct answer, but that is not always going to be the case. So that's one of the major drawbacks of Shor's algorithm, is that there's no way to estimate the value of A. The only clue that you have is that A is smaller than N and that A is co-primary. You cannot say whether what value of A could be correct for guessing this. Therefore, setting a proper value on the time complexity, the upper bound time complexity or algorithm is a little tough because A is a bit of guesswork. So there are more is guesswork. Okay, so are there any doubts up till now? We didn't go through every line of the code since the notebooks will be shared with you. You can have a look at the code later on. We just want to go to the concept, see how it manifests in practice. So are there any doubts regarding Shor's algorithm? That's then the Shor's algorithm. We'll move to Grover's after that.
Yeah, any question? No questions in the chat box, Ansh.
Okay, so
you're done.
Okay, so we'll move on to Grover's algorithm.
Okay.
Okay, so talking about Grover's algorithm. I hope you had you must have seen inside the theory lecture today that the Grover search algorithm is an algorithm which is to find a specific element from an unordered list or an unordered database. So one analogy that everybody uses while considering Grover's algorithm: suppose you have a phone book and you want to find a number corresponding to a certain person's name. So you simply just find the name, which is sorted alphabetically, and you find the number corresponding to that. But what if you want to find the name of a person corresponding to a phone number? So you have to basically go through every phone number, because phone numbers aren't sorted inside the phone number. You have to go through every phone number, and if you have a match with the phone number, you get the name. So that, of course, has a complexity of n, which has a real-time complexity. Grover search claims to do it in kind of complexity of root. So that's a quadratic speedup, which actually means a lot. So Grover's algorithm works on the concept of root amplification. So it has a nice sort of 2D representation we'll be discussing right now. So suppose the state that you're looking for, the state that you're searching for is the omega state or W state, and the equal superposition is represented by the S state. Now, omega and S are not perpendicular or orthogonal, because W is, or omega is, a part of the equal superposition. This is not perpendicular or orthogonal then. But we create another state, say S dash, which is orthogonal to omega, which is basically the state S minus the state omega. So the state S dash is simply S minus
Ansh, can I interrupt for a moment?
Yes, madam. Yes, sir.
Archit wants to leave the meeting because he has other meeting to attend. Thank you, Archit, for your wonderful presentation on QKD implementation. So we look forward for future collaborations also. Even though you are leaving the portals of RVC, but still we need your continuous support. Thank you, Archit.
Thank you, sir.
Thank you, Archit.
Ansh, you may proceed.
Yes. Okay, so this is the thing that we start off with Grover's algorithm. We have some state omega, and then the equal superposition and the orthogonal S dash, which is basically S minus omega. So now Grover's algorithm is an iterative algorithm, which basically works, as said, on the concept of amplitude amplification. So we want to increase the probability of getting the state omega on a measurement. So we have to take the state that was originally over here, the equal superposition, and then move it closer to the state omega, such that when we measure, there is a very high probability of getting the state omega. So that's what we'll be trying to do over here. So that can be done in two steps, known as oracle. The first step is known as the oracle. Second step is known as the diffusion. So we'll discuss each of them individually. So the oracle basically is an operator which reflects the state S about S dash. So basically what it's doing is that it's negating the state W from this equal superposition and leaving everything else the same. So this is the state when W, the coefficient of omega or W, whatever, is 0. And then there is some constant coefficient for omega. And then when you negate that coefficient, you basically take a mirror image of this state S about S dash. So this is the state that you get after applying the operator or the oracle on the state S. Next, we see that it went a little away from omega, so to bring it back to to amplify the amplitude, we apply something known as the diffusion operator. So what the diffusion operator does is that it basically just takes a mirror image of this state, this OS state that we receive, and then it's a mirror image about the state S. So if you see that we're taking a mirror image over here, it would shift by an angle of 2 theta from S, and then you have a cumulative angle of 3 theta from S dash. So we went from having an angle of theta, not accent over here, it's theta over here, theta from angle from S dash. We went an angle of 3 theta in one application of the oracle and diffusion operator. If we apply both of these again, what do we get is, again we take a reflection of our state of S dash. we get 3 theta at the bottom, and then we again take a reflection of this new state about S, and then this reflects about this 4 theta state basically goes the other side. It's 4 theta on top and the theta at the bottom. So you get a cumulative of 5 theta from the original state S dash. So you can see that this is kind of closing the gap towards omega. So we need to apply this multiple times so that we can get as close as possible to omega, so that when we measure this state, we get omega as well.
And there's one question here. Can you give some real life problems that can be addressed by Shor's algorithm?
As Archit just mentioned in the previous session, that the most common, the most prospective application of Shor's algorithm is simply to break RSA. So I don't know how useful that would be, but yes, that is an application for, it can threaten the current encryption policies around the world. Again, it's only for asymmetric encryption algorithms like RSA or Diffie-Hellman. It's not applicable for symmetric key encryption algorithms like the AES 256 and higher. Those are post-quantum cryptographic algorithms, or those are quantum safe, as you may call it. So, yeah, I mean, per se, that is one application that people are looking forward to. How useful that would be is still a question that we don't know what we will do once we have that power to break RSA. But of course, there are other applications that we might actually have if we could also use Shor's algorithm as, say, some as a subroutine inside some other algorithm when it is more efficient and applicable.
Okay, thank you. I think you can proceed.
Okay. So yeah, we saw that applying this diffusion and oracle multiple times closes the gap between our state and omega, and then applying multiple times will bring it so close so that we can making a measurement will ultimately resist it. Now, how many times should we apply this diffusion of oracle followed by diffusion operator? It's simply that every application of these two operators increases the angle between S dash and our state by an angle of 2 theta. So initially we had an angle of theta. Applying it once gave us 3 theta. Applying it once more gave us 5 theta, and then applying it one more give us 7 theta. So every application of the oracle followed by the diffusion will give you an increase in angle by 2 theta. So after k applications of these two operators, you'll have you want an ultimate angle between S dash and the current state to be pi by 2, because that's going to be orthogonal and closest to omega, such that measuring the state will ultimately. So 2k plus 1 of theta is equal to pi by 2. We don't know what theta is yet. We'll talk about that later. So yeah, so now we have to estimate theta. Now there's a bit of math over here going on. So I'll be sharing this PDF with you as well. So you can have a look how we worked out theta, and ultimately we will get theta value as 1 upon root 10. So plugging that 1 upon root 10 into the equation that we saw before, it's basically 2k plus 1 of 1 upon 10 equal to pi by 2. And simplifying this and ignoring the 1 because it's much smaller than the root 10, you get a value of k is equal to pi by 4 root 10. So what this implies is that you only need an order of root 10 operations to find your basically element from an unordered list of say 0, 0, 0 to 1. So that is the speed up that Grover's algorithm is giving, from going from a linear search with an order of n to basically a root n ordered search. So it's not the exponential speed up that quantum computing very often claims to give, but still it's a speed up that is better than the classical version. So that's why Grover's is worth it. Okay, so talk about implementation. talking about the oracle, we saw that, okay, this is another representation which is often used for representing short algorithm. So initially, before applying anything, the qubits are in inclusive superposition. So all of them have an amplitude of 1/2 power n, which is this constant over here. And when you apply the oracle, as we saw, it basically negates the amplitude of the omega state and then leaves everything else the same. So that is represented inside the second graph over here, which is basically you negate the amplitude of omega and everything is the same. Right? So how would you express this transformation as a matrix? So that can be represented as this matrix over here. It is simply an identity matrix for just a -1 in the wth comma wth element. So W is the state that you want to find. Only that is the only one which is going to be a -1. Everything else is going to be 1 as an identity matrix that would invert or negate the amplitude of that one state and leave everything else the same. That definition of the oracle operator, or if you want to put it this way, a size notation would be simply oracle times some state x will ultimately give you x when x is not equal to 0, and x when x is equal to 0. That is one thing that also look at. Next is the diffusion order. So in terms of habits, again, we start off with this after applying the oracle, and then after through the diffusion operator basically inverts this amplitude back as we saw inside the 2D vector representation that we saw before, and then increases the angle from S dash and brings it towards omega. So it's increasing the amplitude of omega such that probability of getting a state omega as a measurement is increased. So that therefore we see that after one application of oracle and the diffusion operator increase the amplitude of this state, and then makes the measurement out the outcome that this is the outcome of the measurement more common. So yeah, that is how it is working. So these are also going to be some values we can calculate based on that. So I didn't do it over here as an exercise. So now mathematically, how can we represent it? So as we saw inside the vector representation, that the diffusion operator simply finds the reflection about the S vector. So the the reflection operator in quantum science is represented by this operator, which is degree 2 of the bra S times the ket S minus the identity operator. This is the reflection operator, which is often used. We have put S over here because we want to find a reflection about the S state. Okay, now this is a little difficult. You can't just simply find reflection about the S state. That's a little difficult implementing on hardware. So what we do is we proceed and succeed it by the Hadamard transform, and then take a reflection about the 2 or about the 0 state. Now this might not be very obvious as to how this works. There's a little bit of proof that I've added over here that that if we were h times 2 of 0, 0 minus 1 is equal to this. You can have a look when we share the PPT to you. But otherwise, the way I look at it is that we're basically changing bases of it. So to change the basis from the Z axis of the computational basis to the Hadamard basis, all you have to do is apply the apply the Hadamard transform, and then the Hadamard transform, the equal superposition for that basis can be said to be the 0 state. So if you can visualize these states on the block sphere, the state is pointing towards the positive Z axis, and the plus state or this state is pointing towards the positive X axis. So you change the basis, and Z became X and X becomes Z. So this is basically X. So 0 is basically in the X basis. So that is how I like to look at it. Is when you first change the basis, do all your operations, take the reflections that you want to take. And again, you take the Hadamard transform. Now, implementing this is much simpler. It's simply 2 times of this matrix minus the entity, which gives you this ultimate. Okay, so let's head to the implementation on time, but okay. Again, as you saw, we have 2 steps, which is the oracle. We saw this already. So creating the oracle is unique for any state that you want to find. So for example, this oracle over here stands for the oracle for 2 qubits to find the state 0, 0. This is also for 2 qubits finds 1, 0, oracle for 2 qubits finds 0, 1, oracle for 2 qubits find 1, 1. However, you're not limited to finding only a single state. You can find multiple states in a single go as well. So this oracle for 3 qubits finding the states 1, 1, 0 and 1, 0. This was about the oracle. And this is the diffusion operator, where this is the definite diffusion operator, which ultimately gives you a unitary similar to this. So we take having both of these operators in hand, we define this function for simulation and displaying the ultimate results. And after running the entire circuit iteratively for multiple times, and we use this oracle over here over 3 qubits. And okay, so let's just represent the ultimate outcome. So this is first of all, this diagram over here is something known as a Q sphere. Q sphere is similar to a block sphere, but this gives you more amount of information. So the dot that you see over here, first of all, represents the state, and second represents the phase of this state. So this is a phase chart. So red over here represents a 0 phase. There's no phase on state 0, 0, 0. So applying the Hadamard gates to get to equal superposition, you get the states are spread across the entire set, all with a 0 space again. The size of the dot means the amplitude of that specific state. So, since the dot is since the amplitude of the 0 state is 1 in the start, it's got a large size, and in the equal superposition it gets smaller. Next, when you apply the oracle, the phase 2 states that we want to find, in this case are 1, 1, 0 and 1, 0, 1 states, go negative. As you can see, the phase is now pi. And then after applying the diffusion operator, the attributes of these two amplify, and all the other states go to 0 in this case. It's not necessary, they'll always go to 0, but it will decrease inside. So, yeah. That's what basically the operation that happened over here is that applying this the diffusion operator simply amplified these 2 states, those amplitudes, and then again change the phase back to 0, and then decrease the amplitude of all of the other states. So that is basically the working of the Shor's algorithm, and this is the circuit which was used to implement. So if you basically find the unitaries for all of for this gate, you find that this corresponds to a similar unitary as we saw over here for the oracle, a similar form of this one, and this over here corresponds to a diffusion operator which has a form similar to this. And when you measure them, you ultimately get these 2 outcomes, which is 1, 0, 1 and 1, 1, 0, with more or less equal probabilities, because those are the 2 states that we are trying to find. Okay, so yeah, that's now these are bits of exercises for you, where you can try different diffusion operators. You can tweak these circuits a little, and then we have printed out the unitaries for them. So you can see that this is the unitary that we implemented over here, and this has a very similar form that we saw over here. There's 1 followed by -1s everywhere. It's 1 over here and -1 everywhere else, and 0 everywhere else. So this is how the unitary works. There is another form of diffusion operator, which is the exact negative of this, which is -1 in the first element and 1 everywhere else. So this is that. This is circuit for that oracle, and the only advantage of this is that the oracle is the depth of the oracle is much smaller. It is much deeper. It has like 1, 2, 3, 4, 5, and 6 gates in a series, while this only has 1, 3, and 4. So this is a whole lot. 5. This is comparatively, at least, it's cheaper in comparison. But this one would increase as the number of users increase. So yeah, that's about Grover, considering the diffusion operator. And of course, we can also explore other oracles as well, finding different states for large number of students. That's again, it's open to exploration. So yeah, that's all that we had for Grovers, and we also had it for Shores. So any doubts regarding anything in Grovers or QFP, QP, anything that you saw?
Sharwani, any questions are in chat?
No questions are there in the chat box, sir.
Okay.
I guess.
Yeah, I think it's a time also.
Yeah.
So participants, probably you're observing the complexity now. I think the heat is high at this moment in terms of how the quantum algorithms should be kind of realized. So Ansh took a lot of interest in explaining the implementation part of the Grover's algorithm. So it is one of the algorithm designed by Indian American scientist Love Kumar Grover. He is not a foreigner actually. So he is from Meerut, from India. So it is one of the game changer in quantum computing space. So I sincerely urge, of course, Ansh will share the Jupyter notebook on the drive. So you please try to run during your leisure time, and also give these assignments to those students who are enthusiastic to go into the quantum computing domain to practice on these algorithms. Even though the algorithms are already available, but understanding all the phases of the algorithm and steps and all, it requires a lot of individual interest. So with this note, I would like to thank Ansh Singal, who is a senior researcher at CIRQUIT, RVCE, who is constantly working in the quantum computing domain, and also he is training many of the juniors researchers. So thank Ansh for such a wonderful presentation, and we will keep up the good work.
Thank you.
And yeah, so more or less IBM Qiskit demos will end today with Ansh Singal's presentation. Tomorrow and day after will not be having any afternoon practical sessions. So whatever you have got so far in the Jupyter notebook, you please try to practice on the platform and try seeing the results. And always you can communicate with them, and they're very helping people. They will try to solve any of doubts. Okay, so the thing is we should work and feel. Okay, that's the only solution for all this stuff. Yeah, with this we'll wind up today's FTP. Thanking Ansh and thanking Sharwani for coordinating the full day program, and Minal. So we'll meet tomorrow at 9:30 for fourth day. Thank you. Have a pleasant evening. Bye bye.
Thank you. Thanks. Thank all the participants.
Thank you, Ansh.
Thank you.
Sharwani, you may stop recording.